Today's speaker is Zhoe Wenbin, who is a good friend that Hugo and I met at a conference in Taiwan quite a few years ago. And now Zhoe is at the University of Nagoya finishing his PhD, which is done under the supervision of Francesco Buscemi, who of course used to be at Cambridge a bunch of years ago. And Zhoe is going to tell us about his really up and coming work on quantum resource theories. So with that, Zhoe, I hand over the virtual floor to you, and thank you very much for coming.
Thank you, David, for the introduction. Hello, everyone. So should I start now? Okay.
Yeah, it's all yours.
Okay. Hello, everyone. So thanks for the invitation and thanks for coming. So today the topic is about resource theory and application in quantum physics, and the subtitle is how to characterize the transformation among resources. And you will know what is this resource theory later. So I'm in Nagoya University, and Francesco Buscemi is my supervisor. So this is my basic information. Now let's get started. Okay, so this is the outlines of today's presentation. Now let's move into the motivation first. So given two quantum states, we're interested in the question, is it possible to transform one into another under a restricted quantum channel? As we know that in the representation of quantum entanglement, the LCC is kind of operational explanation for the definition of entanglement. And this question has been answered was answered in 1999 by Mike Nielsen. He showed that the sufficient and necessary condition for one pure state transfer into another pure state under this restrict LCC. And we also interested in the question that does there exist a state that can be transferred into any other states under this restrict channel LCC. Easily we know that in bipartite entanglement theory, there exists maximum entangled states that can be transformed into any other states under LCC. So then we're interested in the question, what drives the transformation between states? Or what are the conditions for the arbitrary state transformation? It might be because of the amount of entanglement as we quantify the entanglement as E bit. As we see the example of maximum entangled state can be transformed into any other states in the state space. And also it might depend on the class of restrict transformations. And LCC is just one class of the transformations. And maybe there will be some other restrict transformations we might be interested. So and all this the possible answer lies at the core of quantum resource theory, which is the main topic today. The quantum resource theory is a mathematical framework to study quantum physics. Actually, quantum resource theory covers possible all statistic properties of quantum system. You have the theorem of entanglement, you have a theorem of thermodynamics, and etc. All this can be covered in just one unified quantum resource theory. So now let's move into what is the quantum resource theory. So this is a framework of quantum resource theory. I draw a bigger sum, a smaller sum, to represent the more resource and the less resource. And we will have some allowed process to transform from more resource to less resource. And also you have this free resource, which you cannot transfer to any other resource. A toy example is already the entanglement theory with this LCC. We see this entangled state as the resource state, and those separable states as free resource. And also you will need this LCC process, these allowed transformations to transform the resource. And also you will need an entanglement measure to know how much resource a resource contains. So the ingredients are, you have the resource state, you have these allowed transformations, and this allowed transformation cannot generate resource at low cost, or we call this allowed transformation as free operation sometimes. And also you will have this free state. This is the basic three ingredients of quantum resource theory. And one thing to know that there are various ways to define allowed transformations. The one we just mentioned, LOCC, just one of them. You will also have this LOSR, no cooperation with shared randomness, and a DIO and MIO in the resource theory of coherence. And even sometimes we can just use mathematic morphisms to define a transformation. So this kind of platform of quantum resource theory let us study the quantification of the resources and those resource transformations. And there are basically two questions we are interested in. The first one is how to construct the allowed transformations we did for the LOCC in the case of quantum entanglement. And how do we characterize those allowed transformations? So in the following, I will just answer these two questions one by one in different scenarios. I will move to next. So this presentation will be consist of two cases. One is resource theory on the states. The other one is resource theory on the measurement. So the first is resource theory on the states. Back to the first question, how to construct the allowed transformations. And we will use a geometrical approach. So in the quantum state cases, we define the free state first, and then we allow the transformation. Then those allowed transformation is defined as those free state preserving maps. It can be understood as this way. As we will use this notation of resource morphisms to denote the allowed transformations. Basically, this resource morphisms is just a CP-type linear map, what we sometimes call the quantum channel, such that it will preserve the free states as it is. So any state that lies inside the free state will not get out of this set if we apply those resource morphisms. So and one thing to know that we don't need to restrict this free state as separable states as long as it satisfies some mathematic framework, which is the convex of the free state. And you can apply to this free state as this state to a coherent state or even steerable assemblage, etc. As long as all these quantum phenomena satisfy the convex framework. And here we use resource morphism because we don't want to make any constraints on these allowed transformations. We want to use a unified approach to define the allowed transformation. So this structure preserving map, the resource morphism, are considered as the largest set of free operation. If you add more constraints to this resource morphisms, you will have a different allowed transformation. So what we usually call this kind of morphism as maximal resource theory. And with the definition of this resource morphisms, we are able to define a pre-order between the resource. We were able to know which one is more resourceful than another one. So we define this curly inequality between the two states, which means that a state rho can be transformed into a state sigma, of course, up to some approximation. So we don't always have the exact transformation. And there will be some error happens there. And this error is defined by using the norm, the trace distance between two states. So then with the definition of this pre-order, then a very natural thing is this maximum resource element. Just defined as those elements that can be transformed into any other element inside the space. So we have defined the allowed transformation as resource morphism. We have defined the pre-order between two states, which one can be transformed into another. And we have defined a maximum resource element. Now we move into how do we quantify the resources? What is a good measure of a resource? So a resource measure is defined by using these monotonic functions. There are two basic things you have to satisfy. One is you do not increase resource after you apply the resource morphisms, after you apply the allowed transformations. And second, it has to be it cannot be negative because we are using it as a quantification. You don't want to use negative number to represent a quantification of a resource. And it has to be zero for only those free resource. So in the case of entanglement, you have entanglement as a positive number of this quantification, and you have zero for separable state. We will use several monotonic functions for this presentation. So these are three monotons we construct, and maybe the notation here is a bit messy, and the only thing you should remember is just this DH, Dmax, and Dmax F, which are three different types of monotons we define. Both are valid monotonic functions related to the quantifying the resource. So all of them comes from the general running entropy. So you have this DH as hypothesis testing relative entropy, you have Dmax as max divergency, and you have this one as kind of like robustness. So basically a state, it all quantifies how far it is for a state rho with respect to the free sets. So this is the monotons we use to quantify our resources. And then you might ask, why do you consider so many different monotons? The possible reason is that resourcefulness is always a partial order, which means that sometimes you have some, if you define just only one monoton, you will not be able to compare between different resources. So we will need different kind of monoton to define those incompatible states compared to only just one monoton. So this is why we have to use many different monotons. And then this goes back to, then there is another question to ask. What drives the transformation between resources? Given two resource states, as we see here as two sums, rho and sigma, and we know there will be some free operations to allow transformation amount between them, and you want to know which one is more resourceful than another one. Then you may think maybe this is because this can be the reason of the amount of resource, but there are so many different, probably infinitely different resource monotons that are inequivalent to each other. So there is no reason one is always better than another. Then there is a possible answer, of course, if we refer to the maximum resource, and like what we did in the bipartite entanglement, we compare the destinatable resource and those resource cost. For example, if you want to compare the resourcefulness between rho and sigma, you always want to first do the destination of the resource from rho to the maximum resource state or maximum entangled state. Then from the maximum entangled state, you want to calculate how much it will cost to formulate this entangled state sigma. Then this kind of distill and formulation of the entanglement can be seen as a structure to compare to know if one can be transformed into another. And then we can use an example. So as I explained, the resource destination and dilution are very important. And the example is that in the resource theory of bipartite entanglement, if we use this ED to represent the destinatable entanglement and use this EC to define those entanglement cost, and both of these two terms have some lower bound and upper bound. If the lower bound of this entanglement destination is greater or equal than the upper bound of the entanglement cost, of course, the more entanglement you can distill, then you can say that we can formulate a entanglement state sigma, which means the rho can be transformed into sigma. So basically, this lower bound and upper bound can give us a lemma to say if rho can be transformed into sigma or not. But sometimes, because we use this idea of maximum entangled states, and sometimes when maximum resource state or maximum entanglement does not exist, such as in the resource theory multipartite entanglement with LCC, do you have a better answer? So until now, I've explained the background, and let's move into the main theorem. So which is how we characterize those allowed transformations. So this is the first main theorem given to arbitrary states, rho and sigma, and up to some approximation. Rho can be transformed into sigma is characterized through these two monotones comparison. So we don't need to define the maximum resource state or not. We only need is just these two monotone comparison holds. So then this one is less restrictive compared to previous one. Previous ones we used this floor here on this to do the comparison, but this condition can be relaxed to a more less restrictive condition. So with this condition, we can do better than the previous ones. Then because we chose DH and Dmax as two different kinds of monotones, and actually this is very crucial as because we have possible many number of equivalent monotones. The takeaway message for this theorem is that you can quantify the resource without distillation or dilution from the maximum resource. This can be understood in a daily life silly example. For example, you go to the supermarket, you have 1 kilogram of rice, then you have another 1 gallon of milk. You want to compare if one is more valuable than another one. The normal way we do is to use currency, but here you don't need to do that. You just use the kilogram and gallon as two measures to compare them. So of course, this is a very silly example, but it kind of gives you a sense why this theorem is kind of interesting. So here we use DH and Dmax F. Of course, we will be able to use different monotones. So then this goes to next theorem. Now we use Dmax here instead of Dmax F, which is kind of a similar definition of monotone. But we have to satisfy some additional condition. This is a very special case derived from the main theorem, and it will be useful for the application in the quantum physics. So in general, the whole picture is that we search for conditions that are expressed in terms of resource monotones, and we compute them separately. We want to decouple. We don't want to you compute them together. So separately compute them, and for the initial and axial, and we compare the monotones to see if one state can be transformed into another state. So now we can move into the applications in quantum physics. So this is also a widely used example. Consider an input system with initial state rho and a free singleton free set. and the output system with a target state sigma and the free singleton state. We use F prime to denote different system. So now by applying previous theorem, we're able to see that if dH and dmax can be comparable between rho and sigma, then we're able to say that rho can be transformed to sigma up to some approximation. So then with a little physics interest, we can view this singleton as Gibbs state or a thermal equilibrium state. Sometimes in resource theory, we call it free state. And the free operation, this free operation as allowed transformation, we define it as Gibbs preserving operation. So this is a little interest in physics by applying to the theorem we introduced previously. So previously we have introduced only the sufficient condition. Now we're interested in, can this sufficient condition become necessary? It could be so, but it has to satisfy additional condition, which is not just something random. This condition, for example, we have a special case when this alpha is maximum resource state. For example, in the entanglement theory, it satisfies this condition, and then the sufficient condition becomes necessary. So we are able to characterize this transformation between two states through this monotone comparison. And then this DH just can be seen as this resource, as a resource destination, and D max F prime can be seen as a resource cost. So if a cost is, if a destination is always greater than a cost, of course, then alpha can be transformed into sigma. So in the case of this one. And for the destination case, it's the same. It also holds if the destinable resource is always greater or equal than the cost of the resource. But we don't restrict this to a special case. So alpha needs not to be maximum. For example, if you want to distill your state to some special state, not only to those maximum state, as long as this alpha satisfies these two these conditions. Normally this condition can be translated as it is satisfied for pure states. Okay, we have introduced a sufficient and necessary condition to characterize these state transformations. Then we will move into the measurement. So previously we discussed about the state transformation, and those states does not. I have to emphasize that those states does not only need to be the quantum state. It can be coherence or steerable or anything in quantum theory. So now we move into a very specific example on measurement, quantum measurement. Then we answer the same question for the framework of resource theory. So we want to know how can we construct the allowed transformation. Since now the measurement is a very operational phenomenon, so then those free operations, those allowed transformation is also defined under a operational approach. So for a quantum measurement, there will be some pre-processings and post-processings. We can see those processings as just noisy channels. These kind of processings combined together lead to a transformation between them. So now if you want to compare to quantum measurement, here we use POVM to represent the quantum measurement in the most general case of measurement. So we define this curly inequality to denote the transformation from rho to sig from P to Q. So you have this Q here, and it is represented by some pre-processing or post-processing, and with some shared randomness. of course, you can also see this pre-processing and post-processing as encoding and decoding in the coding theorem by Shannon. Then we are able to define those free states, those trivial POVMs as those POVM that is proportional to identity. This kind of trivial POVM does not make any sense because it does not depend on the input quantum states. No matter what you put inside this measurement, it will give you the same outcome. So we call this this kind of POVM, this kind of measurement as trivial ones, because it can be just simulated through some classical physics. Then the free operation, of course, which is the one of the ingredients for the quantum resource theory, is defined. So this free operation does not create a non-trivial POVM from the trivial POVM. So giving you some, without any resource, without any resource or any code, you cannot generate a useful POVM. Then we have defined the transformations between two quantum measurements. Now we're interested in how do we characterize those transformations? What does it mean in some sense for those POVM or measurement transformations? So this is another theorem which is similar to what we have derived for the general case in the quantum state. And now, two POVMs P and Q, one can be transformed into another is completely characterized by this guessing games. What is this P guess? P guess here is just as I draw in a picture here. So given a message X, you do some encoding, the red one here, then you send this encoded message to the measurement, and after you get an outcome, you decode your message through this orange box as a decoder. So this is origin in Shannon coding theory. So we characterize this measurement transformation in terms of coding theory. So then this p-guess, of course, is defined as a maximum guessing probability, the best strategy, or best encoder and decoder you can find to get your best guess, x hat compared to x. So then this transformation between the measurement is characterized as this guessing ability in a game scenario. Then we can actually extend this scenario to a family of measurement. Then if we talk about the family of measurement on this kind of same idea, then we are able to talk about the joint measurability in this paper here. For the time's sake, I don't expand this idea. But the idea is pretty similar to the single POVM, single measurement cases. Now this brings to the end of the presentation. I have explained what is the general case of quantum resource theory. I have given a most general case in terms of quantum states for the quantum resources. Now I talk about the special measurement cases in terms of quantum resource theory. And we characterize those transformations between the resource in terms of, firstly, we do with the monotonic comparison, monotonic function comparison. Now for the special case, with operational meaning, we do with the p-guess, the guessing probability. So then this is the takeaway message. So we derive the unified resource theory that deals with resource transformation, and we apply the resource to quantum measurement. And we showed several applications in physics. And one last message, which I think is most interesting, is what I have explained in previously with this silly comparison between 1 kilogram of rice and 1 gallon of milk. So you can quantify resources without using the distillation or dilution, or equivalent, you can say, without using the currency. that brings to the end of the conversation. Thank you so much. And if you have any questions, I would like to answer.
Okay, thanks a lot, Joe, for this very interesting talk. Obviously, this is very exciting up and coming results. Just meanwhile, people who want to ask questions, put a request under the Q&A button. Maybe I'll ask one or two questions. The first one was like a question on one of the earlier slides. If you go up to where you define your various distance measures.
Okay, so you're talking about the monotones, right?
Yeah, exactly.
Okay.
Yeah, here. So just to see if I've got this correctly, you said that you will need different monotones because some monotones will like not be able to distinguish between certain states.
Yes.
Could you give me like an intuitive example of this?
So mathematically or just
yeah, no,
okay.
I mean both would be the best, but anyway you like.
So I will explain in mathematical language. So normally normally when we talk about this resourcefulness, this comparison between two states, they are kind of the partial order. So what is partial, which means that you have two states, you don't know if one can be transformed into another. So given two states, rho and sigma, and given a definition of this allowed process, let's say LOCC, you don't know if one can be transformed into another. For example, in the case of multipartite entanglement theory, if under LOCC, we know that for this special case of maximum state, like the white state and the DHZ state, both cannot be transformed into each other. So we say that they are incomparable under this special LOCC because they cannot compare with each other. So this is a very easy example to understand why we need a different kind of monotones. Because if you define different types of monotones, maybe you're able to compare them. Like what we did here, we defined these resource morphisms. Then under these resource morphisms, we in our paper, I didn't mention here, but in the paper we mentioned that from this GHG state, you will be able to transform to the W state under this the resource morphisms.
And so, how would those resource morphisms look for that example?
For this multiple entanglement, so it will be the maximum resource states as I explained here. So this morphism is just a mathematical definition. So then how we define this resource morphism? So this typical resource morphism is defined as measure and prepare channel. So you first you measure state first, then you prepare another your target state. Okay. So what we define is like this: is measure and prepare channel as this resource morphisms. So for example, you can measure your GHG states first, and depends on your outcome, you do the preparation for the W state or the white state, as you call it. Yeah. So this is a typical example of how to understand this resource morphism in terms of the partial order.
Then I can prepare any state, right? I can just measure any state and then prepare any target state.
But the thing is that you have to satisfy. So yes, it is true you can prepare and measure any, but you have to satisfy that it will preserve the free states. Okay. So if you have this condition, then it's not that easy, right?
Right. Okay. Yeah, thanks. That's a good explanation. I don't know. Do we have any questions showing up? Hugo, do you have a question?
Yeah, I have a question. Well, wait. So you mentioned that there can be a comparison between resource theory and entanglement, and so we could potentially use resource as a measure of entanglement, with it being 0 when there's no entanglement and it being
Yeah,
something maximal resource when there's maximal entanglement. With
yes.
every measure of entanglement, there is a downside. So with concurrence, tangle, or every measure that I know, there's a downside where there's some state that can be defined where the measure of entanglement falls apart and there's no perfect measure. Does this one have a downside as well?
That exactly defines this theorem. So we have used several types of monotones and to quantify those resources. And we actually don't consider the special case for entanglement. So I don't know if you consider the special case of entanglement, you will have some downside with this specific definition of what we used.
I mean, is there a case where you could have an entangled system that would give you a resource of 0?
Oh no! So I didn't mention that. So the monotone we defined here. So where is it? What we call I forgot the name. So it has to be 0 for all free states, for all non-entanglement states. It is not 0 when it's entangled state. It has to be positive when it is not entangled. So this is called faithful of this monotonic function. As far as I know, the DH and the Dmax and Dmax F are faithful. So for DH, I'm not quite sure. I believe it's so, but I have not proved it yet. But for Dmax and Dmax F, it is faithful, which means that for any entangled state, it has to be positive.
Mm-hmm.
And
then does this also work with maximally entangled states and basically everything, or like these partially entangled states? If you have multipartite systems where you have one set that's maximally entangled, another one that might be maximally entangled, but between the two, they're completely separable. Do you have any strange things that would happen in those situations?
So I understand what you're talking about. So here, we are able to prove that if you consider this multipartite entanglement theory under this framework, we know that there exists maximum entangled state here, which are GHG states.
Mm-hmm.
So the maximum, but we are not sure if there exists some other. So GHGs can be proved as this maximum entangled, but we are not sure if there exists some other class of state which also satisfy this maximum resource monotone. So under this framework, in the case of multipartite entanglement theory, those GHGs they are defined as the maximum entangled state. By the definition of it can be transformed into any other free states under these resource morphisms.
Okay.
Mm-hmm.
Then I have another question related to your first theorem.
Okay.
So you mentioned that here you can use 2 monotones.
Uh-huh.
Yeah, so you mentioned 2 monotones to, I guess, describe your system. Is this only for a bipartite system? Or
no, it does not. It works for any system such that those free states, those separable states, is defined as a convex set, and as long as the convex, and in our framework we only consider the finite dimension, so it's convex and closed. As long as it satisfies this condition, such as the theorem multipartite entanglement also satisfy this. Also the coherence state also satisfy this, and the steerable states also satisfy this. So as long as it's convex and closed, then this theorem should work. So this is just a mathematical framework, and we define. So if you look at the graph I gave you, this F here. So this F can represent anything. Here you can use the example of bipartite or multipartite, as long as it satisfies the convexity.
And the dimensionality you say is finite, but it doesn't have an upper limit, right? It could be anything.
Yeah.
As long as it's finite. Okay. And then you only need 2. You only ever need 2 monotones to describe any multipartite and high dimensional system.
Yes. So the 2 we used here is we actually use 3, but depends on your scenario. So the most general case is DH and D max F. If you consider a special, I think I write it here. So DH and D max here, because the reason is that when we define, if you're familiar with robustness, we have this kind of general robustness compared to the robustness. So there are 2 different kinds of robustness. So this relates to that. So we use D max and D max F. Until now, we have used 3 monotons to compare but for 2 state, of course, you only need 2 monotons. Yes.
Okay. Well, there's so many results here. We could talk for a long time, but I think probably it's time to conclude this talk now. So thanks everyone for tuning in. Many thanks to you, Zhoe, for giving this presentation and for staying up this late in Japan. We're now gonna transfer into our standard group meeting. So anyone who wants to stay for our normal group meeting, please just stay on the channel, and I'll promote you to a panelist. And those of you who are not in the group normally, then see you next week.